The construction innovations Mr. Joseph Strauss achieved for the Golden Gate Bridge project were numerous. The way the workers connected the massive cable, standing on top of the world. And most importantly, the way they constructed the giant towers. For the tower construction, American engineers invented a beautiful machine, the climbing derrick. Check out how these two stiff-legged derricks arrange the steel cells. What's fascinating is that after completing one layer of cell construction, the derrick can climb up and sit on the cells it had just constructed. From this new increased height, the derrick can once again assemble the next set of cells. The question here is, how exactly did the American engineers make such gigantic derricks climb? Take a look at these huge plungers which provide support for the derricks. To climb upward, the workers first had to attach a cat head frame onto the last piece they had assembled. Now, observe this clever pulley motor arrangement. After this arrangement was complete, the workers operated the plunger supporters at the bottom, which were disconnected from the towers. If they operate the motors, the entire arrangement will climb upward. In fact, it required 10 minutes for the traveler to be raised up by a distance of 12 meters. Notice the perfectly prefabricated reinforced slot present in the height. Once the 12-meter climb up was complete, the workers activated the plungers, locking them into the new slot. As seen earlier, the derrick starts to build the tower from this new height. What's going on in these double-deck scaffoldings? Millions of rivets are needed to connect the cells of the towers. First, the workers must heat up the rivets. Then, the rivets are transported to the top of the tower using an innovative pneumatic method. The way workers connected the neighboring cells is illustrated here. The tower's riveting work was mostly done from the inside. After the assembly of one level is complete, the next set of cells fit on top of the bottom cells as illustrated. Workers can now start the riveting process to connect the block vertically. In order to reach the tower work area, workers used these built-in elevators. If you've ever enjoyed a stroll on the Golden Gate Bridge's pedestrian path, you may have noticed a small door on the tower. It might be difficult to believe, but the towers in the bridge have tiny lift elevators inside them, which are mainly used for inspection purposes. This means that during cell assembly, the engineers had a plan for the provision of the lift. The dazzling Golden Gate Bridge is supported by the towers we just constructed, and those towers are supported by a strong underwater foundation. You may be wondering how exactly they constructed the foundation in the first place. As you can imagine, considering the rough ocean currents, construction of such gigantic concrete structures was not an easy feat. Indeed, this is where divers with engineering skills came to the help of this project. Initially, they constructed a temporary bridge on the south side. To build a strong foundation for the bridge, the divers first had to convert the lopsided ocean bed to a flat, horizontal one. An easy method to achieve this is to simply drop some dynamite bombs onto the ocean bed. Can you guess what would happen if the dynamite on the ocean bed explodes? Most of the explosion's energy would be absorbed by the water, leaving the structure of the seabed largely unaffected. In order to get the best results out of an explosion, the dynamite should be placed deeper in the seabed and not at the surface. This way, the soil will absorb the majority of the explosion's energy. The next issue that comes up, however, is how to keep the bomb inside this hole. Because these are timed bombs, a human diver cannot do this task. If they are unable to place the bomb before the timer goes off, you can imagine what would happen. Mr. Joseph Strauss came up with a clever solution to this problem: the use of explosion tubes. The divers first aligned an explosion tube exactly above the hole, which would facilitate placement of the bomb. Once the bomb was lowered in, a controlled portion of the seabed could be exploded efficiently and safely. The divers' work was not over after the blast. They also had to clear loose material from the seafloor using high-pressure hoses, and sometimes assisted the dipper dredge in cleaning the debris. After many such blasts and lots of cleaning, they finally achieved a perfect ocean bed like this. Now that they had the perfect canvas, the divers could start assembling prefabricated steel structures on this bed. Because oxygen tanks for divers had not yet been invented in those days, the divers could only breathe underwater thanks to long tubes from the surface. After an exhausting assembly operation that took almost 6 months, the foundation's steel structure was finally ready. The divers then covered the steel structure with wooden forms. Alas, it was time for concreting. The entire steel structure needed to be filled with concrete. Gigantic pumps could feed the concrete to the steel structure area, but a devastating construction failure would ensue. To understand what will happen, let's do a small experiment.
Here I have a small underwater construction, but using the normal cement. Let's see what will happen if this cement comes in contact with the water. I am removing the casing. You can see the cement is spreading. It's just spreading too much. It's looking beautiful, right? The spread. The pillars are standing there, but the normal cement just spread everywhere.
The same issue would happen in the Golden Gate Bridge site also. The concrete would mix with water, and it would not remain within the structure, compromising the entire construction effort. Now, let's see the solution.
Here I have used a special cement called PCC. This is again after half an hour of settlement. Let's see how does this new foundation behaves when it comes in contact with the water. This is staying strong and stable. It's spreading a little bit but not too much.
A similar cement, which is suitable for marine conditions and with high workability, was used in the Golden Gate Bridge foundation as well. The underwater concreting was done with the help of a technique called tremie concreting. The tremie pipe is a long but segmented pipe. The concrete is transferred via these pipes. You can see the tremie pipe is attached with the crane. Interesting thing is that during the concrete transfer, the tremie pipe is lifted continuously up. This way, the concreting starts from the bottom, and it proceeds layer by layer. This way, the chance of water contact is reduced. You can see that our special cement with admixture has become quite strong after 12 hours of settlement. All they had to do next was pump out the water. The thick wall they constructed is currently sitting on a weak seabed. Ideally, a foundation should sit on a strong bedrock called hard strata. Let's see how to lower the huge concrete structure by 15 meters. Mr. Strauss initially constructed a thick, reinforced concrete slab so that workers could continue to work beneath it. Because the ocean currents are so rough, the fender wall could collapse at any time. Therefore, the concrete slab acted as both a safety structure and as a support for the fender wall. Mr. Strauss placed the worker's shaft and the material shaft inside the fender walls. Interestingly, the workers reached the worker's chamber via a worker's shaft. They continuously drilled the boulders and dug underneath the RCC slab. Did you notice this small pipe? The purpose of the pipe was to constantly supply air to the chamber, preventing the chamber from filling up with water. In fact, this is a compressed air arrangement which keeps the pressure inside the chamber greater than the water pressure outside, preventing water seepage. During this process, the entire fender wall structure could slowly sink lower into the seabed. You can see its knife-like shape. Eventually, they reached the rocky, hard strata. After leveling the hard strata, they constructed a steel structure there and built an RCC foundation. The construction of the complete foundation was quite easy to achieve after this point. You can see how the fender walls protect the main foundation from the deadly Pacific Ocean waves. The engineers could now construct the towers on these foundations, as we have previously seen. Before erecting the tower, they first leveled the top surface of the concrete pier. To do this, they laid down a thick steel plate on the foundation. Next came the cellular assembly of prefabricated pieces. Some details of the cell geometry are shown here. However, toward the end of the tower, the cranes lifted a peculiar shaped structure called a saddle. The enormous cables of the Golden Gate Bridge passed through it. With the tower fully erect, the workers sat at the top of the world. A bone-chilling experience. However, the work was far from over. One major task remained: installation of these cables. The main cable is in fact made up of 27,000 smaller steel wires with a total length of 129,000 kilometers. To lay out these cables, workers constructed a catwalk bridge for themselves. At first, workers laid a support wire. The main cables made their journey across the bridge via these spinning wheels. These small wires were passed over the tower through the cable saddle one by one and were then clamped by workers. The workers then pressed the wires tightly using a hydraulic press. They simultaneously wound the wires together using galvanized steel wire, which is why the main cable looks like a single large pipe rather than a collection of small wires. These cables are anchored to the bedrock with strand shoe steel plates. Once the main cables were mounted, the suspension cables were attached to it. All that was left to do was construct the deck structure and lay down concrete for the road. Did you know that the proposal for the initial road deck of the Golden Gate Bridge was something like this? A double-decker design. Isn't that beautiful? Unfortunately, this design was rejected because constructing a double-decker bridge would have significantly increased the cost and engineering complexity of the project. Next, they had to construct the road deck structure, which was also quite a challenging task. To facilitate the process, workers prefabricated each member of the truss and brought them to the site via ships. Assembly of the individual members was accomplished using a derrick, and their connections were secured via rivets. To ensure workers' safety in case they fell, a net was installed underneath the bridge deck. As the construction of the bridge progressed, they simultaneously connected the structure with the main cable using suspension cables. Moreover, to maintain equal loading on the cable, workers assembled this system simultaneously and equally in two directions for each tower. Finally, the Golden Gate was bridged. A whopping 250 pairs of vertical cable were used, securing the entire length of the bridge deck to the main cable. After the construction of the steel structures, the workers painted the bridge a special international orange color. Here are the details of concrete road construction on top of this solid structure. Workers first laid down wooden formwork. They attached steel bars, welded them to the steel sections below them, and later poured and compacted the concrete using a needle vibrator. The Golden Gate Bridge in San Francisco, California has a total of 6 vehicle lanes. There is also a dedicated pedestrian walkway on the eastern side and a separate bicycle lane on the western side that provides safe passage for pedestrians and cyclists, allowing everyone to enjoy the bridge.
What a beautiful bridge, also huge cable. You may be aware that Jaes is fighting for a survival. Currently this channel is surviving thanks to support our Patreons. So if you can become one of our Patreons, I would truly appreciate that. Thank you for watching the video. Take care. Bye bye.